Today we're going to look at Chapter 6, Waves and Sound. So we need to share. Go. Slideshow. There we are. Waves. The chapter title just says waves, but we're going to look into waves, both light and sound. All right. We know that matter doesn't just sit there and do nothing. Matter tends to be easily disturbed, and some matter can disturb other matters. That always involves motion. Something has to move. And when something moves, right, we've already learned that when something moves, a force is involved and work has been done. Right, so that means energy is involved. The energy has to be expended in order for something to move. And when we say matter is disturbed, we mean that the matter is not in the same position as it was before. So when we apply energy to matter, that disturbance can come in several different forms. But the simplest form is like drop a pebble in calm water on a pond, say. And you'll notice that from that point of impact, you have disturbance, waves moving out from that point. I suppose we need to define what a wave is. The wave motion that we're describing does carry with it energy. We added energy to the matter by dropping the stone, and now the energy that we imparted to the matter is being carried away from that point of impact by the wave. We're going to define wave quantitatively in just a few minutes. Now we're just getting a feel for what waves are. Everybody has an intuition about ocean waves. Right? The water's moving up and down, correct? So we know what a wave is. Or if you see a boat driving through the water, from the bow of the boat, and actually from the stern as well, you get waves propagating out from the boat. But waves can come in many different forms. Sound waves, of course. We recognize sound, and electromagnetic waves also are waves. Electromagnetic waves are also known as light. But waves can travel through the earth as well. Seismic waves, earthquake waves, come in two main forms. And now we even have instruments that are designed and built and have been able to detect gravity waves, changes in the force of gravity in a periodic motion like you would see with a wave. And these detectable waves have been identified as propagated from the impact of two black holes. Okay, so what does wave motion do? Well, waves do transfer energy, but generally speaking, they don't transfer matter. In other words, the energy propagates outward, but the matter through which the wave propagates doesn't move, at least not substantially. In other words, as the wave propagates, like this, then the molecules just move up and down. They don't move side to side. At least not in any appreciable amount. So what we're saying is that the wave form is in motion, but the matter is not. So the wave propagates, matter stays put. And you can see that if you say place a cork on still water and then drop a pebble, say a foot or two away from it, and you see the waves propagate out. And when they get to the cork goes up and down, but it doesn't move side to side. It doesn't follow the wave. It just moves up and down as the wave passes. Similarly, earthquakes do the same thing. I mean, if an earthquake happened and a wave traveled through the earth and the wave itself caused earth motion, then we'd have a pretty messy place to live on. So waves can travel through different types of matter. Water waves through a liquid, earthquake waves through a solid, seismic waves through a solid, sound waves through gases. But sound waves can also travel through liquids and solids. It's just what we normally associate with sound waves travels through gas or air. The electromagnetic waves, though, the radiation that we associate with light, travels through empty space, right? There is no matter. So one way of thinking about electromagnetic radiation is it carries its own medium with it. But technically speaking, there's no mass there. It's just the radiation travels through empty space. Now, light can travel through matter, and when it does, it interacts with that matter. So the speed of light in a vacuum is one speed. The speed of light through, say, a diamond is much slower. We're not going to try to explain that right now. Now, waves can be single pulse, like the stone dropping in the water, hits once and the wave propagates out, that's it. Or the wave can be generated in a periodic motion, such as a violin string under a bow. So as the bow is drawn across the string, it continuously causes the string to be stretched and released and stretched and released. It vibrates continuously. It's a periodic motion. Okay, now we can classify waves based upon how the wave propagates through matter, or no matter for light, of course. One type is called a longitudinal wave, and the other is called transverse wave. And that has to do with the displacement that's observed as the wave propagates. Right? So for a longitudinal wave, particle motion and the direction of the wave are both parallel, longitudinal. So in other words, if this is the direction of the wave, and it's going to have a certain velocity, of course. Remember, velocity is a vector quantity, so it has both speed and direction. Well, the wave itself propagates in the same direction. It's the movement of the wave is in the same direction as its velocity. So how do you do that? Right? We can't draw like this because that means the wave propagates perpendicular. Right? If it propagates in the same direction, what you see is a compression and rarefaction. So this will be close together, this will be close together, this will be close together, and then these would be far apart. And so you get a compression and a rarefaction, we say. As opposed to, and sound is that type also. Think of it as a push-pull, or a spring. If you have a spring and you pull on it and release it, then you'll see propagating down the spring a compressed region, and behind it a stretched region, compression, rarefaction. So it's a push-pull, often called a compression wave. And that's the type of wave that sound is. That's opposed to a transverse wave, like the one I drew earlier. So if the motion of the particles is perpendicular to the direction of the wave, that's a transverse wave. Whereas this is on longitudinal wave. Okay? Now, that's why we said earlier, or I said earlier, that there's no motion of the particles relative to the wave motion. In this case, the motion of the particles is perpendicular, so they don't move in the same direction as the wave. But with longitudinal waves, you have compression and rarefaction. The particles do move in the direction of the wave, but they return. They move that way and then they come back. They move that way and come back under compression and release. So the bulk movement of the matter for either wave is net zero. They don't move, they don't change position over the long term. Light is a transverse wave. In fact, light is a combination. We call it electromagnetic for a reason. Light is electromagnetic because there's a component that runs this way, the electrical field component runs one way, and then into and out of the board, let's see, sort of like that, is the magnetic component. Electromagnetic wave means that it has two parts to it. It has an electrical field strength change, and it has a magnetic field strength change, and they're perpendicular to one another, and both are perpendicular to the direction that the light moves. This is a better representation, this animated GIF here. Okay, so we see the light moving in this direction, and we see that as it passes this point, you see an decrease in the electrical field and the magnetic field perpendicular to one another. Now, earthquakes produce both types of waves. They produce both longitudinal and transverse waves. Okay, so this represents the longitudinal wave for sound. In other words, here's the compression, here's the rarefaction. Whereas light is a transverse wave. Okay, now we're going to start introducing quantitative quantitative variables for wave description. Then the wavelength, represented by this Greek letter, the small letter lambda. Okay, that represents wavelength. And It's simply the distance between one complete wave. So from this crest to that crest is a wavelength. Notice that we have motion high here and then low in the opposite direction here and then back up here. So you have to measure it from the same relative position. This height, this crest to this crest. You could measure it from this trough to this trough. Or you could measure it from where it crosses going up to back over here where it crosses going up again. As long as you have the same reference point, the same type of reference point, you can measure the wavelength. All right. Then there's also the amplitude of the wave. That is, how high is that crest? Or if it were a longitudinal wave, how much compression is there before the rarefaction occurs? Okay, that's the amplitude of wave. It's the maximum displacement of any part of the wave from its equilibrium position. And the equilibrium position here is represented by this straight line. Right? It's not the distance from this top to this crest to this trough. It's the distance to from the equilibrium position. And this is also interpreted as the manner in which energy is transmitted in a wave. So the energy transmitted by this wave is directly proportional to the amplitude squared. Right? So if we double the amplitude, if it's this high and then we go, and then we have another wave with the same wavelength that goes, it's twice, say this is x and this is 2x in height, then the amount of energy transmitted by that wave is actually 4 times the original. And that's what that means. Directly proportional to the amplitude squared. All right, we talked about wavelength. Now we can introduce the topic of frequency. So if we take a snapshot of the wave, we can say the distance between this crest and that crest is the wavelength. Okay, we can look at it another way. Suppose we fix our gaze on a point. Here, right? There's your eyeball looking at that point. All right, and count 1 second. How many of these waves of that wavelength, how many of them pass that point in 1 second? That's the frequency. So the number of waves that pass that point in 1 second has a special unit of measure called the hertz. Okay, which is actually equal to cycles per second. And cycles is really a dimensionless number, right? Cycle can be any size, so it really has no meaning. So the actual unit of measure for hertz, if you convert to hertz, we convert from hertz, is seconds to the -1 power, which means it's in the denominator, right? In case you need to do unit conversions later, then you know what hertz is equal to. Right? 1 hertz is 1 cycle per second. Now, what's a cycle? A cycle is from here to here. Right? How many of those in 1 second? Right? If it's just one wavelength passing in 1 second, it's 1 hertz. Another variable or characterizing term for a wave, we call it a period with a capital T. This is the time it takes for a wave to travel the distance of one wavelength. How long does it take for this one to go to here? Count the amount of time. How long does it take for that wavelength to travel one wavelength? Well, actually, if you know frequency, you know period. Or if you know period, you know frequency, because they are inverse of one another. Right? This is how many cycles pass a point in 1 second. But this is how long it takes for one wavelength to make the distance. So that relationship is useful. Frequency equals 1 divided by period, or F equals 1 divided by T. Right? So T is in seconds, frequency is in reciprocal seconds. So if you take the inverse of T, you get reciprocal seconds. So the units of measure match on both sides. All right. So if a wave has a frequency of 4 hertz, then 4 full wavelengths will pass in 1 second. So how many seconds does it take for one cycle to pass? Well, take the inverse of frequency. The period is 1/4 second. One wavelength will pass the point in 1/4 of a second. Okay? Because 4 wavelengths pass a point in 1 second. Then in 1/4 second's time, only one of those wavelengths has passed the point. All right, so this is just a composite of the definitions we've offered so far. Wavelength here, period of time for one wavelength to travel that distance, and frequency. See, there's period again, period there, and frequency then for this one is 4 hertz, right? 4 wavelengths per second, and this one is twice that much, 8 hertz. Notice as the frequency increases, the period decreases by the same proportion. If we double the frequency, we cut the period in half. Now, how fast is this wave traveling? It's useful to know how fast energy travels from one place to another. And that's what we're actually saying about a wave. All right, we know that speed is distance times time. And then for velocity, of course, we add the vector direction in there. But if velocity is distance divided by time, then one wavelength is the distance it traveled, and the period is how long it takes it to get there. So a wavelength divided by the period is the velocity. Remember, period is in seconds, wavelength is in, well, standard measure would be meters, meters per second. But we know what T is equal to, right? T is equal to 1 divided by frequency. So if we substitute in here 1 divided by frequency, then that's in the denominator. So we get lambda f. So the speed of the wave is the wavelength times the frequency. And let's see if that's true. The wavelength is meters. Frequency is hertz, or reciprocal seconds, remember, which is equal to meters per second. Right, so our units verify the calculation. All right. Here's an example. We're going to talk about a sound wave. The sound wave we're investigating has a speed of 344 meters per second. And that's pretty close to what it would be in air at sea level and at 20 degrees Celsius. So if the frequency is 20 hertz for problem A, we got two problems here. Problem A is 20 hertz. Problem B is 20,000 hertz, right? K, kilohertz. What's the wavelength of each of these sound waves? All right. So if we say velocity is equal to wavelength times frequency, and we know that the velocity is 344 meters per second, and we know that 20 hertz is the frequency, right? Then all we have to do is say, all right, this is going to be that divided by this, right? Yes, these two cancel, leaves us with meters. So 344 divided by 20 is, let's see if I can do this in my head. Let's see, 34.4 divided by 2 is 172, correct? 17.2 meters for 20 hertz. Yeah, they rounded it off. Okay, that's right. Because 20 hertz only has two significant figures, and we're assuming that there's a decimal there. Okay, so how about 20,000? Well, really all we need is for this one to be 20,000 instead. So that means this one has to be divided further by 1,000. 1, 2, 3, 0.0172 meters. 1.7 meters times 10 to the 10 to the minus 2 meters. 1.7 times 10 to the minus 2 meters. Right? So there you go. All right. There's another exercise. Let's say the speed of sound is the same as before. Only now we know the wavelength is 0.5 meters. What's the frequency of the wave? Well, if we know the frequency and the sound, we just solve for the wavelength. Oh, wait a minute, excuse me. We know wavelength. Now we solve for the frequency. So we need 344 divided by 0.5, which is the same as multiplying by 2, which is 688 hertz. Okay, there's 688 hertz. All right, we associate, we have an intuition about sound. If the frequency increases, then we detect that as an increase in pitch, right? So what would 688 sound like? That's pure, 688 hertz tone, okay? And if you've ever played a musical instrument or played in a band or played a piano for that matter, the standard note is A440. The A note on the keyboard tuned to 440 hertz. And this is what it would sound like. Okay. So 688 is a higher frequency. It had a higher pitch. A440 has a lower pitch because its frequency is lower. All right, now let's look at electromagnetic waves. These are the kind that don't need matter to propagate. I mentioned earlier the electromagnetic waves, or light, consists of vibrating electric and magnetic fields, and they both oscillate perpendicular to the direction of the wave motion and perpendicular to one another. So one goes this way and the other one goes this way. And we know what the speed of light is, at least in a vacuum. And we give it this special letter, C. Right? C. To an approximation, it's 3.00 times 10 to the 8th meters per second. Actually, it's 2.9979 times 10 to the 8th meters per second, to 4 decimal places. And that's in a vacuum, but it's a very close approximation to the speed of light in air. Now, when I was in school as a kid, we didn't use the metric system very much, and the speed of light was 186,000 miles per second. So we could relate to that. But in the sciences, of course, we're in the metric system, so we need to use the metric system wherever possible, unless you need to make a conversion, and there you have an equivalence. This is equal to that. So you have a conversion factor if you need one. All right, and this is what it would, this is a graphical representation of a beam of light with oscillating electric fields, magnetic fields, and the propagation direction toward X. Now, the eye, in our case, the human eye, is able to detect changes in light frequency, and the brain interprets those changes, the electrical signals that are generated through our retina, into the optic nerve and transmitted to the occipital lobe, where light information is interpreted. We see those colors as, we see those different frequencies as color changes. But we only see a narrow range of wavelengths. Right? Visible light is very narrowly defined, in the neighborhood of 400 nanometers to 700 nanometers. So the red end is the longer wavelength, and the blue end is the shorter wavelength. And the unit of measure here commonly used is the nanometer. And it's used simply because we want to avoid decimal points. So if we use a nanometer, that gives us 3 whole numbers, 3 whole digits with no decimals. And this very closely approximates the wavelength of the color of light which is being investigated. So what's a nanometer? Right, let's get our terminology straight here. A nanometer, a milli is 1,000th. So a millimeter would be 10 to the minus 3rd meters. A micrometer, a micrometer, would be 10 to the minus 6th meters. A nanometer is 10 to the minus 9th meters. So 1 nanometer for the wavelength change would be 10 to the minus 9th meters. So if you have to do a calculation, for instance, where we equate the speed of the wave with wavelength times frequency, this would be like that. But the wavelength You can't use nanometers because the speed of the wave is in meters per second. So if you have to make a conversion, if you have to solve the equation, then you would have this one would be equal to the wavelength would be whatever the nanometers are times 10 to the minus 9th meters. So this value times 10 to the minus 9th. And then the frequency would be reciprocal seconds. So you have to be careful when you're using this formula that you have the correct units of measure. Meters here instead of nanometers. We use nanometers for convenience, but for the calculation, it has to be meters. All right, so here's an example. What's the wavelength of the radio waves produced by a station with an assigned frequency of 600 kilohertz? Right? So 600 kilohertz, that's an AM station, right? AM versus FM. AM stations are in kilohertz, FM stations are in megahertz. So 600 kilohertz would be the frequency right here. And this is a constant, so you can solve for the wavelength. So here's your frequency, kilohertz, which has to be converted to hertz, right? Because frequency is in reciprocal seconds. And kilohertz is not reciprocal seconds. Hertz is reciprocal seconds. So 600 kilohertz, and here's the way I like to make the conversion. If we have 600 kilohertz, take that value. What does kilo mean? It means 10 to the third, 1,000. So this would be 600 times 10 to the third from here, hertz. Right? So that's why it's 600 times 10 to the third, or 6 times 10 to the fifth hertz is the frequency. Rearrange the equation for our unknown, right? And then you just divide by rearranging, divide this value for the speed by the hertz. And we find that the wavelength of the radio wave being used at that broadcast frequency is 500 meters. That's pretty long, isn't it? Radio waves have a very long wavelength. 500 meters to go from one peak to the next peak. Okay, so here's an example of an AM 800 kilohertz, FM 90 megahertz. Right? So mega means a million, which means you would need to multiply this times 10 to the 6th power hertz before you used it in the formula. So notice that with this relationship, as the denominator frequency gets bigger, we have a higher frequency. Say we go from 8 times, go 10 to the 5th up to 10 to the 7th. So that's 2 orders of magnitude roughly. As the frequency gets bigger, the wavelength gets smaller, right? If this gets bigger, then that quotient gets smaller. We increase the size of the denominator, so the speed of light divided by the denominator then makes a smaller number. So as the frequency increases, the wavelength decreases. All right. So visible light waves occur in the range of 10 to the 14th hertz. Let's go back just a second and look at that picture. Okay, there's 10 to the 14th. 10 to the 15th would be right here. So 10 to the 14th would be low end, let's see, 2018, 14, 12, 10, 8, yeah, okay, 10 to the 14th hertz, and then increase slightly, not even 10 to the 15th. And that's our range for hertz of visible light. Let's see, where was I? There we go. So visible light has relatively short wavelengths. Remember, high frequency, short or low wavelength. So the wavelengths of visible light is very short. For instance, here's one at, let's see, 10 to the 4th, 10 to the 14th. So that'd be the red. Exactly 10 to the 14th would be red. And here we're leaving out the 3 times 10 to the 8th, just to give us a ballpark idea. So visible light has a relatively short wavelength in the order of 10 to the minus 6th meters. Okay, 10 to the minus 6 meters, very short. 1/1,000,000th of a meter. Okay. And we talked about nanometers a little earlier, so I'm not going to beat this horse anymore. So that's the visible range of light. So which end would be red? The longer wavelength is the red end. The shorter wavelength is the blue end, right? And we all know, well, at least I remember, how to remember the order of colors, right? Going from red to blue. Right? Red, orange, yellow, green, blue, indigo, violet. So this direction would give you 700 nanometers here and 400 nanometers there. Okay? Now, how bright it is just depends on how much energy is included. In other words, what's the amplitude of the wave? Now, what's beyond this section down here? Well, this is going to be ultraviolet, right? Comes next. And on this end, infrared comes next. Okay? Here we go. So there's infrared beyond the red. And then you get microwaves that you use periodically to heat your food or pop popcorn. Then your radio waves. Actually, AM should be on the other side over here. AM shortwave FM. Because FM has a higher frequency. And on the other end, ultraviolet, and then you get to X-rays, which everybody has experienced at one time or another, either in the dentist's office or perhaps X-raying a broken bone or what have you. And then gamma rays, the most energetic class of light waves in the universe. Okay, let's get back to where we were. Sound waves. Okay, we're going to look at sound in a little more detail now. We're going to come back to light, not in this chapter, but when we start talking about, when we get to the chapters on astronomy and the universe, then we'll get back to talking about light. But for now, we're going to leave that subject and move to sound. Right? So sound is a compression wave. In other words, a longitudinal wave. So you have areas of compression and rarefaction. And that's the way that the wave propagates in the same direction as the velocity of the wave. All right, so here's an example, this tuning fork. So when this fork, due to the way it's constructed, will vibrate at one frequency, and one frequency only. And as it vibrates, it moves the air around it, right? So this side will move out and compress, and then move back and rarefact. So that movement of the tuning fork produces the compression wave. Now, because the bar on the tuning fork is so narrow, it's not very efficient. It doesn't move a lot of wave as you go. So you either have to hold it close to your ear, or you have to set the tuning fork on a box of some kind that's designed to take the vibrations from the tuning fork and transfer them to larger air movement. That's why pianos have soundboards and guitars have flat tops. The strings can't move very much air, right? They're not wide enough. They can vibrate at a characteristic frequency depending on the tension and where you stop the string, but and the mass of the string, of course. But they don't move very much air. So a piano without a sounding board, or a guitar without a flat top, you wouldn't be able to hear it. So that's why we attach the vibrating string to a larger surface so it can move more air. Okay, just like electromagnetic radiation has a spectrum, a visible spectrum, where we can see from red to blue, or actually violet, from red to violet, the sound has a spectrum also, which our ears are tuned to detect. And we won't talk about the physiology. This is the wrong course for that. If I were teaching you anatomy and physiology, then we'd go into the structure of the ear and explain how the ear detects those vibrations. But for now, just take it on faith that our ear is generally tuned to receive and interpret wavelengths from around 20 hertz, 20 cycles per second, up to 20,000 cycles per second. That's our normal hearing range. Some people can hear outside that range. And other species definitely can. So infrasonic would be a lower frequency than 20 hertz, and ultrasonic would be greater than 20 kilohertz. Now we know dogs can hear higher frequencies than we can. That's why when you blow a dog whistle, you can't hear it, but it definitely registers with the dog. Infrasonic sounds, very low frequency sounds, sometimes we can feel them as vibrations, but they can actually be heard and interpreted as sound by various marine creatures, whales, for instance. So this is another interpretation of the audible region. And the compression waves, as they strike your tympanum, or the eardrum, they cause a series of events to take place, vibrating little bones, which transfer that vibration to a fluid, which enters the inner ear and causes a specific type of electrical stimulation in your auditory nerve. That's the best explanation I can give you in one sentence. Okay, now we have, how do we quantify sound? I mean, we can register through instrumentation the frequency of the sound. But for health concerns, we need to know something about the loudness of sound, right? Because very loud sounds can damage your eardrums. So we can express loud, soft, relative, qualitative interpretations. But that doesn't give us the type of information we need to make sound engineering decisions about our environment. So this term, intensity, expresses that in a quantitative fashion. Intensity is the rate of energy transfer through a given area. So if you have an area here that's mapped off, say, a square meter, and sound is impinging on that square meter, then we measure how much energy is transferred through that square meter. So the energy that transfers through that square meter is a measure of intensity. It's often called flux. Flux implies motion through an area. Okay, so that's a quantitative. We know how to measure energy. We know how to measure the area, and we just measure the amount of energy that's transferred through that area, and we have a quantitative value for intensity. So the more energy that's transferred through that area, the more intense the sound. If we take the same amount of energy and transmit it through an area 10 times that size, then the intensity is 1/10 of the original. So I haven't explained this before, and I'll do it now. Quantitative measurements in the sciences can be subdivided into two groups. One is the intensity. An intensity factor means that no matter how much of something you have, the value is always the same. Density is a good example of that. So if you have more, say you say the density of iron is 7 grams per cubic centimeter. Then if you have more iron, say if you have a larger iron ball, the density doesn't change because you've also increased the volume. So intensity factors are independent of the amount of substance. Whereas capacity factors do depend on the amount of substance you have, such as mass, volume. The intensity here in this measurement is an intensity factor because it doesn't matter how much power, overall power you have, because you're translating that power through an area. So if the intensity is a certain level here, then if the intensity is the same for a larger area, more energy is going to be transferred through that larger area. Right? Many textbooks will say, we'll call this intensive versus extensive. Now those may be accurate terms, but they're not intuitive, right? I have no idea what extensive means. Not based on the word itself, but I do understand what capacity means. So that's just to let you know that you may run into these terms rather than those terms. And these two mean the same thing. Okay, so intensity is measured as the amount of energy transfer through an area, right? And in fact, this is the time rate of transfer. It's the measure of rate of energy transfer. Right? So it's not just the total amount of energy transferred, it's how fast does it transfer. And that is power. So energy or work in a certain amount of time is power. So intensity is derived from power transferred through an area. That's why the unit of measure here is the W, or watt per square meter, or joules per second per square meter. Both are valid. Now, to give you some intuition about what we mean by this intensity, the threshold of hearing for most young people, you sort of lose this ability as you get older, but the threshold of hearing is taken as 10 to the minus 12 watts per square meter, which is very low. It's just a whisper. Whereas an intensity of 1 watt, right, 10 to the 12th times, right, that's, let's see, a million mega, giga, tera. A terawatt per square meter is painful to the ear. So you have a wide range. You can just barely hear something at 10 to the minus 12 watts, but if it makes it to 1 watt, then you experience pain. Well, this measurement of intensity is valuable, especially where research is involved, because it's easily quantifiable and it can be converted. Units can be converted from one form to another, because we know the relationship among energy, power, time, area. We know all those conversions. So the conversion is easy. But it's difficult to use those values for everyday safety concerns, measurements of sound. And we'll get to that unit of measure in just a second. Let me see, let me catch up with my let's see here. Okay. Another important rule, or actually a law, that you need to keep in mind is that as sound propagates out in all directions from a source, well, as it moves out, the area that it has to cover increases, correct? Right? It's like the surface of a sphere. So as the sound wave moves out, then it spreads to the equivalent of the sphere at that distance. So the surface area of a sphere is 4 times pi r squared. So if you know the distance from the center of the sphere, then you can calculate the area. Well, notice that whenever you double the distance from the center, you increase the size of your sphere by double, you have squared the area that the sound must cover, right? This is related to what's called the inverse square law. So as you increase the area of your sphere, you spread that same amount of energy, the power, in other words, you spread that power out over a squared area. So this inverse square rule looks like this, right? So at this position, say that's a square meter. Well, if you move out another meter, if you go 1 meter here, if you go another meter, 2 meters, you double the distance here to here, what happens? Well, the area now is from double from this distance to that distance has increased by 4. If you triple the distance, then you increase the area by 9. So the intensity of the sound as you get farther away decreases as the square of your distance. Now, a more practical scale for measuring intensity is the decibel scale. Deci means 1/10. So the decibel unit is 1/10 of a bell. So we need to know what a bell is, I suppose. Well, the bell is a unit of intensity that was named in honor of Alexander Graham Bell, the inventor of the telephone. But the bell is a very large unit, and it's not very useful for measuring intensity and making judgments about intensity. So we actually define the decibel. Now, you don't have to know what that definition is. You just have to know the relationships among the different levels of the decibel. First of all, the decibel scale is not linear. So a sound that is doubled in intensity only increases the decimal by 3. So each time you double the intensity, you increase the decimal value by 3 units. Right? So if you have 30 decibel sound, and then you measure another sound that's 33 decibels, then the intensity here increases to twice the value there. So this intensity increases from here to here, doubles. All right? Now, here's the scale, and this came straight out of your book. Here's a scale for the decibels, right? The threshold of hearing is marked as 0 decibels. So 0 decibels is the same as, what was it? 10 to the, let's see, intensity. 10 to the minus 12 watts per square meter. Equals 0 decibels. Actually, that should be a capital B. There you go. All right. So where's the threshold of pain? Well, let's see if we can find it. Right. Average home, conventional, city, average factory, subway, rock, riveting machine, jet plane, rocket launch. I think, here it is, 120 decibels. So 120 decibels is the threshold of pain, and we said earlier that that intensity equals 1 watt per square meter. So between 10 to the minus 12 watts per square meter and 1, you have a range of decibels 0 to 120. Unfortunately, even though we can say these are equal, we can't use them easily as conversion factors because the decibel scale is not linear. Whereas the intensity scale is linear, but the decimal scale is not linear, so we can't make a direct conversion there. We have to use a visual scale indicator to make our conversions. Now, there are ways to do it, of course, but that's beyond this course. All right, we mentioned ultrasound earlier. ultrasound is anything above 20,000 hertz. Yes, 20,000 hertz. The human ear typically cannot detect that, with some exceptions. Some people are able to detect it, but for the average ear, above 20,000 is inaudible to humans. But that doesn't mean that ultrasound isn't useful. We may not be able to hear it, but we can use it because we can build instruments that both generate sounds with higher frequencies than 20,000 and receive that information in a detector and then interpret it for us in a visual fashion. So that's where you get the use of ultrasound in diagnostic examinations, where you get the jelly that's smeared on some part of your body and you have this magic wand that rolls over it and generates a picture. They're using ultrasound, ultrasonics, to get a picture of some internal organ. The nice thing about it is it's not as potentially hazardous as X-rays. I've also used ultrasound to clean laboratory instruments. There are special pieces of equipment that are built with ultrasonic generators inside. Right, there'll be a tank here and a fluid there. Could be water, could be some other fluid. And then you have a generator here that introduces high frequency, greater than 20 kilohertz, vibrations into that tank. And anything you put in there will be impacted with that energy wave and hopefully dislodge any dirt. Okay, ultrasonics are also used in nature by some animals who use it to navigate their environment and find their prey, bats in particular. They use high frequency sound waves to get a picture of their environment. They know where objects are, like this wall. They know where insects are that they can find to eat. Now, why do they use ultrasonics and not normal sound or infrasonics? Well, for one very good reason. The higher the frequency, the finer the detail. In other words, you can see smaller objects with higher frequencies. And you can distinguish between two different objects that are close to one another with higher frequencies. Now, the only reason I put this description down here in yellow was this is a theoretical basis for that. It's called the Rayleigh criterion. In other words, the angular displacement of two objects or the angular size of an object that you can detect depends upon the wavelength of the sound or light, for that matter. So as you decrease the wavelength, you increase the frequency, correct? You decrease the wavelength, and that way you're able to see smaller angular differences. So if you have something over here, some object over there, and you want to distinguish it from a second object, then the angular displacement of the two is like that. So if they're at this distance and you move them farther away, the angle becomes narrower. So the closer they are, the larger the angle. And the closer they are, the easier it is to see them. Well, it's also that angular distance separating the objects, or the angular width, is easier to detect with shorter wavelengths. So ultrasound is a better choice for bats for their echolocation than normal sound or infrasonics. Okay, the speed of sound. We mentioned earlier, when we worked problems, the speed of sound was set at 344 meters per second. But the speed of sound does vary based on the material and the environmental conditions. So the speed of sound in air is approximately that 344 meters per second, or 770 miles per hour. That's at 20 degrees Celsius and 1 atmosphere pressure, which is approximately a fifth of a mile per second, right? Or a third of a kilometer per second. If you increase the temperature, then the speed of sound increases. So if we go from 0 to 20 degrees, the speed of sound increases from 331 meters per second to 344 meters per second. So temperature does make a difference. If we get colder and colder, then the speed of sound decreases. If we get warmer and warmer, the speed of sound increases. Also, the speed of the sound generally increases with density. In other words, speed of sound in water is much faster than it is in air. And it travels a greater distance also, but that's another topic. Okay, about 4 times actually. Speed of sound in water is about 4 times that in air, simply due to the difference in density. And the speed of sound in air will increase with air pressure. So at higher altitudes, the speed of sound is less. Right? In Denver, the speed of sound will be less than it is in Beckley, because we're at lower altitude with denser air. Now, obviously, the speed of light is much faster than the speed of sound. So we can use that difference to estimate how far away a lightning strike occurred. Right? The speed of light is so much faster than sound that it's virtually instantaneous. So since sound travels roughly a mile for every 5-second count, or its speed is 1/5 of a mile per second, that means that for every 5 seconds, the sound travels for a mile. Well, once you see the flash, start counting. 1001, 1002, 1003. If you get to 5 seconds before you hear the thunderclap, then you know that the lightning strike was a mile away. Okay? Actually, it was 4.68 seconds for that 1 mile. So this is a rough estimate. All right. What's the wavelength of a sound wave in air at 20 degrees Celsius with a frequency of 22 megahertz? That is a very high frequency sound, but it can be calculated, right? We just need to know this equals that times that. And we know that this one is 344 meters per second. And the frequency is 22 megahertz. 22 times 10 to the 6th hertz. 22 megahertz, million hertz. Then if we solve for wavelength, it will be in units of meters at 16 times 10 to the minus 6 meters, or 1.6 times 10 to the minus 5th meters. All right, let me check that calculation. Because I don't understand why this value is not in scientific notation. Okay, so 22 exponent 6, and then divide that into 344. That's correct. Yeah, 16 times 10 to the minus 6 is the same as 1.6 times 10 to the minus 5. All right. Now we're going to describe up to this point, we've looked at sound that's been propagated from a stationary source. But now we're going to look at sound that's propagated from a moving source. And the moving source changes the character of the sound that it emits. That's called the Doppler effect. This is an apparent change in frequency, a change in pitch of the sound relative to the motion of the observer. If the source is moving and the observer is stationary, or if the observer is moving and the source is stationary, similar effect. But as they're moving toward each other, what happens is the sound wave on the side of the observer is compressed. And the frequency, the pitch, increases. It's higher. And then as you pass, as long as the source is still emitting, then the pitch of the sound appears to drop as you go past. Okay, that's known as the Doppler effect. Now, the Doppler effect is also observed for other types of waves, particularly light waves. And we'll talk about that one at some point in the future. Okay, so what does that look like? Well, for instance, you hear this moving car, and in order for the Doppler effect to be detected, the movement of the source relative to the observer must be a substantial fraction of the speed. So if the speed of sound is 344 meters per second, then the source would have to be moving some fraction of that, maybe 34 meters per second, maybe 10% of that. I don't know exactly where the threshold is, but it's just a point is made that the source needs to be moving a substantial fraction of the speed of the wave that's being propagated. So for sound, it would be some substantial fraction of 344 meters per second. And what happens is the waves are bunched up in front because emit one wave and it propagates out. And by the time you get ready to emit the other wave, the source has moved closer to the wave that was just emitted. So now the difference between the two waves is shorter than it would otherwise be. That's what this illustration of compression is for. Okay. Now, we use the Doppler effect actually, we use the Doppler effect in radar, weather radar, to detect severe weather disturbances. For instance, if the emitter is over here and it's sending out radar waves, and over here you have a tornado that's circulating counterclockwise, then this tornado has within it water droplets. Water droplets. And on this side, they're moving this direction. And on this side, they're moving that direction. So what Doppler radar does is it bounces radio waves off of these droplets, and the ones that are moving toward it shift the return signal to a higher frequency. So this side will be a higher frequency, higher frequency. And this one will be a lower frequency than was originally emitted. And they use that information to detect the presence of certain types of circulation in the weather structure. That's one way to use the Doppler effect with light waves. Another way is to detect a shift in color, actual wavelength of light from distant objects in our universe. And it turns out that the faster they're moving away from us, the more shifted we are to longer wavelengths. They call it the red shift. And we're going to talk about that a little more when we get to our chapters on astronomy. So I'm not going to labor it right now. So if the object is moving toward you, you get a blue shift in light. If the object is moving away from you, you get a red shift in light. All right. So just as an exercise, I said to myself, okay, suppose we shifted the wavelength from 400 nanometers to 500 nanometers from a distant object. What percentage of the speed of light would that object have to be moving in order to generate that difference? And I just did some quick calculations and determined that in order for that shift to occur from 400 nanometers to 500 nanometers, and 400 is in the ultraviolet, not ultraviolet, it's in the violet range, to a little more red shifted, how fast would that object have to be moving away? In fact, it's a little bit more than the 25% of the speed of light. So it's pretty fast. Okay, another phenomenon, the sonic boom. What causes the sonic boom? Actually, it's related to the Doppler effect. So think of it in terms of a Doppler effect as the emitter, or the vehicle, perhaps in this case, is moving faster and faster. And as the vehicle approaches the speed of sound, the compression waves become closer and closer and closer together in front of the object. that's emitting the sound. So when it does that, when it finally reaches the speed of sound with its forward motion, the waves can't get out of the way, right? They're stacked up on top of one another. You're moving as fast as the sound wave is, so when you emit the sound, it doesn't go anywhere. It just stays right there with you. And they just stack up. Well, what happens is, at that point and beyond, if you move faster than the speed of sound, you tend to stack up those compression waves behind you in the shape of a cone. And when that cone touches the ground, you hear, because those compression waves are stacked up on top of each other, you increase their intensity. So as that cone passes some point on the ground, then you hear this big boom, simply because all of those compression waves are packed up together against one another. So this is what it would look like graphically. Right? So here's your sound that's being emitted by a stationary source. Right? The wavelengths on both sides of the object are equal in length. If your velocity is less than the speed of sound, then they're still going to be stacked up a little bit, and you can detect, as the object passes, you can detect a change in pitch. Okay. If your velocity is the same as the speed of sound, we call that Mach 1, then here you have all your compression waves are going to be stacked up right in front of the plane. Okay. But if you exceed the speed of sound, now you're moving faster than the sound waves can get out of your way, and they form this cone. And of course, when that shock wave strikes the ground, then you get a sonic boom. Now, it stands to reason that you'd get a sonic boom from the nose of the craft, but you also get a sonic boom from the tail of the craft, because it's up here away from the body of the airplane, and it's creating its own shock wave. So usually when a plane passes overhead that's moving faster than sound, you get a double boom. Okay, I've got a little video here that I hope will explain in better than I just did. So let's just take a look at it and see what we come up with. Here we go.
Many aircraft, mostly military, are supersonic. They can fly faster than sound. When they do, they produce a sonic boom. We hear this boom before we hear the noise of the airplane. What makes this sonic boom? And why do we hear the sound of the airplane only afterwards? Sound expands in a sphere. The sound source produces vibrations which travel in all directions as waves of compressed air. Though the sound waves move in 3 dimensions, we can make it clearer if we show them in 2. A white circle will represent a single wave of compressed air. Now here is the sound source, and here is the person who hears the sound. First, the situation where the sound source doesn't move. The compressed waves of air travel in regular succession, equally spaced. The distance between 2 compressions is called a wavelength, represented by this symbol, the Greek letter lambda. This has shown how the compressions expand when the sound source stays in place. But what happens when the sound source is moving? We'll represent the speed of sound by the letter C. V stands for the speed of the sound source. Let's see what happens when the speed of the sound source is half the speed of sound. V equals 1/2 C. When the sound source moves, the waves of compressed air in front of the sound source are closer together. This means that the wavelength here is shorter than the wavelength of a stationary sound source. And behind, the wavelength is longer. Now let's look at the picture when the sound source moves at the same speed as sound, when V equals C. The compressed waves accumulate. They will all reach the observer at the same time. He hears a loud boom. This time, the sound source will move faster than sound, at supersonic speed. For our example, we will have it move twice as fast. Let's say that the observer is on the ground below an aircraft. The wave compressions now form a cone. This is easier to see when we begin to draw in more of the innumerable sound waves that are actually generated. The more waves, the more obvious the cone. On the surface of the cone, the compressions are very close to each other. They combine to form a percussion wave, which a person perceives as a very sharp booming sound. An airplane flying at supersonic speed produces a conic percussion wave, which follows behind it. Wherever the percussion wave hits the ground, the supersonic boom can be heard. Now, at the house on the river. Now, at the house near the woods. The percussion wave produces more than just a loud, startling sound. It can break windows. So to avoid damage and annoyance, aircraft aren't allowed to fly low at supersonic speeds over settled areas.
Okay. So this lost my train of thought. This sonic boom phenomenon can cause damage. And in fact, airplanes that fly faster than the speed of sound have to do so using jet engines. But if air striking the engine as it comes in the inlet, air strikes the engine fan blades at supersonic speeds, it will destroy them. So the airplane has to be built in such a fashion that the air that's impacting the plane slows down before it goes into the engine. And so the ductwork that leads to the engine has to be constructed in such a fashion that the air slows down subsonic speeds before it enters the engine. Otherwise, the whole plane would just fly apart. Okay, there are other ways to make sonic booms, and one of the fun ways that I used to as a kid was cracking a whip. When you spin that whip around and bring it down into a snap, the end of the whip picks up speed as it reaches the end of its turn. It picks up speed, and at the very end, the tip of the whip exceeds the speed of sound and gives you a combined compression wave that we hear as a crack. Okay. Now there's another concept called standing waves. So how do you produce a standing wave? Waves are supposed to be in motion, correct? So how do you get a wave to stand still? Well, it's something of an illusion, actually. A standing wave doesn't really stand still, but the wave form that is attributed to the wave is stationary. And this has to do with a concept called interference. And I've got another video that I think will help explain it better than I can in words. I'll just give you an example. If you attach a rope, or a slinky for that matter, a spring, at one end on the wall, and you start whipping the loose end up and down, there's a point at which you can add energy to that wave in which you will establish what appears to be a stationary wave. In other words, the crests will stay put, the troughs will stay put, and as long as you keep whipping that spring at the correct frequency, it will stand still. Now, when two waves meet one another, and it doesn't matter what the wave is, it can be sound, it can be light, whatever. When they meet one another, as the wave forms past one another, they interact. Sometimes they reinforce one another, which is called constructive interference. Sometimes they may even cancel one another out completely, which is called destructive interference. And then there are intermediate levels in between. Now, when we produce this standing wave, typically you fix the distance between the 2 points on either end. And you add energy at just the right frequency so that you get various wave forms. Now, for a given distance, you can have different wavelengths of standing waves. In this case, you've got one crest here, one trough there, right? So you really only have half of a wave, right? Because the other half of the wave would only come back if you extended that out beyond to another half wave. This one, however, has a complete wave. In other words, if you look at this orange line right here, that's one wave that goes down here and back down here like that. And if you start at the connected point on either end, you have completed one wave. Now, where the amplitudes are maximum, crests and troughs, these are called antinodes. And those places where the wave appears to disappear completely are called nodes. There's little or no displacement at all. So you've got a node in the middle here, and you've got a node on either end. Node here. This one has 2 nodes. This one has 3 nodes. This one has 4 nodes. This one has 2 antinodes. This one has 3 antinodes. Okay? All right. So here's our video, and I hope it will clarify some points for you.
Waves can overlap. When that happens, the highs and the lows can build upon each other, or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So constructive and destructive interference never occur at the same time. Instead, they alternate one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right. Typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay, so standing waves are the basis upon which musical instruments are based. Some standing waves produce that, the standing wave is produced by a vibrating string, or it could be a vibrating column of air in a wind instrument, or it could be a drum for that matter. Hello? Yes, ma'am. Okay. Okay. All right. Appreciate it. Okay, you too. Bye. That was Alan. You're separated at 5. That's the problem. She said, Dr. Gordon, you still want to see. Even though you separated 5, that 4 for just a couple of weeks, that level, I'm not correct. I'm not correct. Okay, so the topic of resonance has to do with how energy interacts with matter. We say that something resonates with a waveform. That actually there is a natural frequency that all objects will vibrate at. And it only resonates when an external vibration exactly matches the natural internal vibration. A good example of that is a swing set. In other words, when a child sits in a swing and someone, an adult perhaps, pushes the child in the swing, they go up and they come back down at a given frequency, because the swing is a pendulum and it has a natural frequency of oscillation. And if you continue to push at just the right time, you can add energy to that oscillation, and the swing will swing higher on either end. But it will still swing at the same frequency as before, just with bigger oscillations. It still swings at the same frequency. That rule was proven centuries ago by Galileo. So what that means is if the frequency of energy input pushing the swing is at just the right frequency, the same frequency of push as the frequency of the swing, then you can keep adding energy to it. And the swing is said to resonate with the person pushing it. Now, these things happen in nature too. The periodic driving force can cause a natural frequency vibration in the object. Sometimes that's desirable for musical instruments, for instance. Sometimes it's not desirable. For instance, for architectural constructions like buildings and bridges. If the driving force exactly matches the natural frequency of the building or the bridge, the forces can build up beyond the structural limits of that construction, and you get a disastrous results. Here's a simple example of resonance. These two tuning forks are exactly the same pitch. Pick a pitch, it doesn't matter, as long as they're the same. Say this one's set for A440 and this one's set for A440. If you strike this one, then the vibrations of air coming out of the sound box below this tuning fork will be transmitted through the air to the sound box over here and cause this pitchfork, this tuning fork, to vibrate at its natural frequency, because it's being stimulated, energy is being introduced to it at the same frequency as its resonant frequency. Okay, like I said before, musical instruments are naturally tuned to various frequencies, and the musical instrument, of course, can be its resonant frequency can be changed depending on the note that's produced. So for pianos, the resonant frequency depends on which string you strike. for violins and other stringed instruments, the resonant frequency depends on first the tuning of the instrument at the beginning when you tighten the string, and then where you stop the string at various lengths, you change the natural frequency of the string. For wind instruments, you change the length of the tube that is vibrating the sound. But each one of these processes, these procedures, changes the resonant frequency of the instrument to suit the note that is to be played. Okay. This is the next to the last slide, and it's another video which is one last hurrah for a resonant catastrophe.
Hey, I'm Grady, and this is Practical Engineering. Today, we're diving into one of the classic case studies of engineering failure, the Tacoma Narrows Bridge. This video is sponsored by the Great Courses Plus. More on that later. A bridge is a quintessential civil structure. Humanity's need to get from one place to another without getting wet is as old as history itself. And for so many years, there was one force with which bridge engineers had to contend: gravity. The fundamental question of bridge design was this: how can we hold up the structure itself and all the people and vehicles that may cross it against the force of gravity pulling them downward? And secondary to that, how can we do it economically for the least cost to the public, since most bridges are funded by the taxpayer? So over time, bridge designs evolved with our understanding of structural engineering and ability to create better construction materials into lighter and more efficient shapes, one of those shapes being the suspension bridge. A suspension bridge is essentially just a deck, two towers, two main cables, and connector rods which suspend the deck, hence the name. The primary advantage of suspension bridges is that they can so efficiently span long distances with only two towers, reducing the amount of material required and, more importantly, the cost. This advantage of being able to span long distances while minimizing material gives suspension bridges their iconic slender and graceful appearance. But that same lack of material reduces the rigidity and stiffness of the structure. Where before bridges were generally stiff enough that gravity was the only load that needed to be considered, now a new force started to impact their designs: the wind. In July 1940, the Tacoma Narrows Bridge opened to traffic between Tacoma, Washington, and the Kitsap Peninsula. At the time, it was the third longest suspension bridge in the world. Financing construction of the bridge was a major obstacle, which led the state to pursue an innovative design. Rather than the originally proposed trusses, the bridge used two narrow plate girders to stiffen the deck, giving the bridge its iconic steel ribbon appearance across the Puget Sound. Unfortunately, that analogy extended beyond its appearance. Even during construction, it was apparent that the bridge was too flexible, even under moderate winds. Construction workers gave it the nickname Galloping Gertie. Only 4 months after it opened, the bridge collapsed in dramatic fashion. In fact, this failure was so dramatic, there's a good chance you've seen this video before. So what's happening here? You've probably heard of resonance, which is where a periodic force syncs up with the natural frequency of a system. The classic example is a swing. With resonance, small periodic driving forces, like pushing someone in a swing, can add up to large oscillations over time because energy is stored. In the case of wind-induced motion, the periodic driving force comes from an effect called vortex shedding. This is where fluid flowing past a blunt object oscillates as vortices are formed on the backside. When these alternating zones of low pressure occur at a frequency near the natural frequency of the structure, even small amounts of wind can lead to major oscillations. This is why some chimneys are equipped with helical vanes to create turbulence and break up the vortices. The day of its failure, the Tacoma Narrows Bridge did experience resonance from vortex shedding. You can see this in the vertical undulations for which the bridge was famous. But this resonance isn't why it failed. About 45 minutes before failure, a different kind of oscillation started. You can see in the historical footage that right before failure, the bridge isn't oscillating vertically, but in a twisting or torsional motion. The reason for this change in oscillation is still debated, but one of the best suggestions has to do with the aerodynamics of the bridge. Rather than a truss through which wind can flow, the shape of the Tacoma Narrows Bridge, with the large steel plates on either side, created some strange interactions with the wind. Any small amount of twist in the bridge created vortices, or areas of low pressure, in locations that actually amplified the twisting motion. Each time the bridge returned to its natural state, its momentum twisted it in the other direction, where the wind could catch it and continue the cycle. This phenomenon is called aeroelastic flutter. It's the same reason that a strap or sheet of paper vibrates in the wind. It's a completely separate mechanism than resonance from vortex shedding because the periodic forces are self-induced from the naturally unstable aerodynamic shape of the bridge. This flutter eventually created too much stress in the suspension cables, and the bridge failed. One way that modern bridges avoid flutter is to include a gap in the center of the deck so that the pressures on either side can equalize. I cut a slot in my model, and sure enough, the vibrations almost completely stopped. Another option is just to make the bridge deck more aerodynamic to avoid creating vortices that push and pull on the structure. Of course, bridges aren't the only civil structures affected by the wind. Take a look at the very first practical engineering video about tune mass dampers to learn about how wind-induced motion can be mitigated in skyscrapers. For a simpler example, take a look outside at just about any high-voltage power line. You might notice small devices hanging near the insulators at each pole. These are stock bridge dampers that help suppress wind-induced vibration on long cables and signs. And of course, other types of engineers contend with flutter as well. I've heard that airplanes are designed for wind loads, but I can't confirm it. These days, we have a much better understanding of the variety of loading conditions that can be faced by bridges and other structures. But much of our current understanding has come from failures of the past. The case of the Tacoma Narrows Bridge is a well-known cautionary tale that's discussed in engineering and physics classrooms across the world. The main lesson isn't necessarily that you should make sure to consider aeroelastic effects when you design a suspension bridge, even though you definitely always should. But I think more importantly, it's a reminder of how profoundly capable we are of making mistakes. When you push the envelope, you have to be vigilant because things that didn't matter before start to become important. Unanticipated challenges are a cost of innovation, and I think that's something we can all keep in mind. Thank you for watching. Hey, I'm Grady.
All right. So the last slide is just a reminder of information that was covered in the chapter today, and the main topics have to do with velocity equals wavelength times frequency, the relationship of frequency to period, and of course the speed of light. And that's it for chapter 6.